So I wanted to conclude briefly the story about crystal structures and lattices by discussing one additional concept, and this is the concept of nearest neighbors. So if you're in a crystal structure or a lattice and you position yourself on top of an atom or a point of the lattice, then you can look around yourself, and the very important concept, particularly, I mean, when we're going to discuss in the future electronic structure and all that, is the concept of nearest neighbors. That is what you see immediately in your vicinity, in the vicinity of yourself. How many atoms you see at a given distance from yourself, if you position yourself in a given atom. Let me, of course, start with the usual example of the square lattice. If you're in a square lattice, right, and you position yourself in this point, right, an obvious question is to ask yourself, how many nearest neighbors do I have to myself? What is the answer to this question? 4, right? It's 1, 2, 3, and 4, right? So you have 4 points or atoms, 4 points at a distance, if this is A, at A. However, you may also wish to ask yourself, what is the next shell of nearest neighbors, second nearest neighbors? So we call these ones first nearest neighbors. But what about second nearest neighbors? How many do we have in a square lattice? 4, right? We use colors. I have this one, this one, this one, and this one, right? So you have 4 points at square root 2a. And so on and so forth, of course, right? I will have third nearest neighbors, fourth nearest neighbors, and so on and so forth. This is very important as a concept because, let me anticipate what we're going to discuss in a few lectures. When we're going to consider this point as an atom will have a charge distribution. The charge distribution will have some exponential tails. And these exponential tails are going to overlap with exponential tails of the wave function, the atomic wave function coming from another atom, right? So if I want to determine the overlap or the interaction between the electronic states of these two atoms, it is important for me to know that this charge density is going to overlap with a given set of nearest neighbors, primarily, right, 4 nearest neighbors, and then to some extent, to a lesser extent, also with the charge density of the other second nearest neighbors, and to an even less extent with the charge density of the atoms that are far apart. Okay, so proximity, geometrical proximity in a lattice is a very important concept because wave functions decay exponentially. So it is important for us to know which are the atoms that are close to every given point in the lattice. There are, of course, other reasons. If you were going to discuss in the future vibrations. So vibrations are dynamics of atoms, and the dynamics of atoms is determined by the interaction between neighboring atoms. You can expect that there's going to be an interaction between this atom and this atom, but not between this atom and an atom located somewhere here, of course, right? The fact that an atom here exists is not really relevant for an atom sitting here because there's no interaction between the two. They don't feel each other. Okay, so it's very important to classify neighbors as a function of the distance from a given point in the lattice. And of course, the concept of the lattice is very important because if I sit on this point, I will see exactly the same environment. So once I do it for one, I have done it for the whole crystal, essentially. I don't need to repeat it for every point in the lattice because the lattice repeats itself periodically. I guess this is all obvious concepts. So what I would like to do now is just give you a couple of examples of nearest neighbors in more complex lattices than this one. The obvious next example is the triangular lattice in 2 dimensions. Don't ask me to draw it again. If you have a triangular lattice in 2 dimensions, how many first nearest neighbors do I expect for a triangular lattice? 6, right? It's 6 of them. You have an hexagon surrounding each atom. Can you imagine what is the number of second nearest neighbors for the triangular lattice? You can look at your notes if you wish and take a look at the triangular lattice and see if you can come out with some ideas of the number of second nearest neighbors for a triangular lattice. Can anybody tell me what? Don't ask me to draw it again. I mean, it's too complicated. How many second nearest neighbors do we have in a triangular lattice? You sure? Do I need to draw it? Huh? Okay, good. All right. Okay, so I sit here. So the first shell of neighbors is, I'm using the red color now, 1, 2, 3, 4, 5, and 6, right? What about the second shell? And the distance is A. Well, here we have to be careful, right? It's there's this here. What is the distance between this point and this one? Remember, these are all equilateral triangles, right? So what is the distance between here and here? 2 square root of? If this is A, what is this? These are all equilateral triangles. My question is, what is the distance between this point and this point? Square root of 3, not 2. This is 120 degrees, right? So this is the square root of 3a. How many equivalent points like this green one do I have around? This one, right? You noticed, I mean, this is the one, this line is going through the middle of the segment between two nearest neighbors, right? So this one, whoop, here, this one, whoop, here, whoop, here. 6. Of course, now I have to ask myself, what about this one? What is the distance between this point and this point? 2a, right? So it's slightly longer than this. So this is the next shell, the third shell. And I have 6 of them, right? Oops, there's another one here, of course. There's this one, and there's this one. Okay? So you have 6 nearest neighbors, 6 second nearest neighbors at square root 3a, and 6 third nearest neighbors at 2a. And of course, I can continue growing. All right. More complicated line. Now we go to 3 dimensions. Simple cubic lattice. How many nearest neighbors?
4.
Simple cubic. 4 or 6? 6. You're here. Well, it's getting messy. I hope you Yeah, I hope you can see it. Whew. Well, anyways, I mean, if you sit here, you're going to have the 6 points that are along the Cartesian axis, right? Here, you just move along the Cartesian axis, the 3 Cartesian axes minus and plus A, and you'll find neighbors. So there are 6 nearest neighbors at distance A. What about second nearest neighbors now? It's a bit more complicated. You say 12. Anyone else? 4. Well, let's see. Where are they? What about this one, for example? What is the distance between this point and this point? Square root 2, right? So let me color it with green. What about this one? It's the opposite corner of the cube. So square root 3. So it's not the second nearest neighbors. So you see, I mean, I'm moving along the square on the plane. So definitely I'm going to have the 4 points that are on the x-plane, right? xy plane, sorry. 4 points. But I can do this exercise for the 3 different planes, right? I can do the same exercise if I take the yz plane, and I will have this one, this one, this one, and this one, right? They belong to the xy plane, and they are also at distance square root 2. Finally, I can do it for the xy plane. And I have this one, this one, this one, and this one. Right? So it's a total of 12. You were right. So I have 12 nearest neighbors located, located on the 4 in each of the 3 independent planes, x, y, yz, and xz. Okay, so it's 6 nearest neighbors at A, 12, sorry, first nearest neighbors, second nearest neighbors at square root 2A. And then the next shell is the one at square root 3. How many? 8, right? I need to look for the corners of the cube. These are the corners of the big cube, of the cube of side 2A. So I have 8 of them. Third. Right? These are all the points that are, let me use the orange. Here, here, well, down here, well, they're all the points located in the at the corners of the big cube of side 2A. There are 8 of them. There are 8 corners in a cube, obviously. And then, I mean, I can proceed further. What about BCC? BCC, you have a cubic lattice, a simple cubic lattice, an atom at the center. Now, you could sit on the, okay, let me do it here. And then we have another atom at the center here, right? And then, of course, if I sit here, I have to consider that I have, I'm surrounded by this, right? So if I sit here, where are the nearest neighbors? What about this one? This is at distance A. Same, right? What about this? The one at the center. What is the distance between this and this? square root 3 over 2a, smaller than 1, right? So this is the first nearest neighbor. This must be the second nearest neighbors. Hmm? You don't like it? Do you accept it or not?
Okay, I accept it, but
I don't understand. What don't you like of this?
okay. Usually, okay, okay. At the center, we put okay, a basis, right? And was
Well, BCC does not, I mean, let's see it as a Bravais lattice. And BCC is a Bravais lattice, so we don't need to talk about basis. We talk about a lattice. In fact, I'll use this concept in a second. So the closest point to this one is this one. But this point is not alone, right? How many of these points are there surrounding this one? 8, right? Because I have 8 equivalent cubes surrounding this point. This is just one. This is just one octant. There are 8 more octants in all the other directions. So if I sit here, I will have 8 first nearest neighbors at the distance square root 3 over 2a. Now, there's another way to see it, and in fact, it's exactly to exploiting the concept that this is a Bravais lattice. If this is a Bravais lattice, this point must be equivalent to this one, right? There's no difference because they both belong to the same Bravais lattice. So if I sit on one or if I sit on another one, around myself, I must see exactly the same configuration. And if I sit here, now it becomes obvious that I have 8 nearest neighbors. I don't need to imagine, I mean, constructing 8 cubes around me. I just sit here, I look around myself, and these are the 8 points, right? In fact, if I sit here, I should construct the cubes centered here, and these points here would be the centers of the cubes, when I start from this as an origin. Another way to say this is that BCC can be seen as 2 simple cubic lattices that are interpenetrating, right? So you have one simple cubic lattice, you have another one which starts from here and continues and is formed by all the points that are at the centers of the cubes. They also form a simple cubic lattice, right? So whether I sit here or I sit here, I see around myself exactly the same environment. I see 8 points, and these are the 8 points that lie at the edges of this cube, at the corners of this cube, if I sit at the center, of course. If I sit here, I will see exactly the same. And these points will be the edges, the corners of the other simple cubic lattice that forms the BCC lattice, right? Because the BCC lattice can be seen as 2 simple cubic lattices that are interpenetrated, one into the other one, right? So I can start from here and build a cubic lattice using all the points at the centers of the cube. And that would be also a cubic lattice, a simple cubic lattice, obviously. All right, so I see it, I could see it starting from here, but I see it much better if I sit here, and I see now 8 nearest neighbors. And that's equivalent, because I know that this is a Bravais lattice, so every point is exactly the same. What about second nearest neighbors? How many do I have? Now it's probably more convenient for me to sit here to find out the second nearest neighbors. What are the second nearest neighbors? 6, right? Because these are all the points, so let me use the usual notation is to use red for the nearest neighbors. So I'm using now this as the center. So this is the first nearest neighbor. There are 8 of them. Second nearest neighbors is what? Green. So I'm using green, this, and all the points along the Cartesian axis, right? So there are 6 of them. So I have 6 second nearest neighbors at distance A. And so on and so forth. Finally, FCC. FCC. and then I have to place points here, 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 in the back, and here. Let me sit here. Where are the first nearest neighbors? And how many? Right. This distance is A. This distance here is square root 2 over 2A. Right? So it's smaller than 1. So this is the nearest neighbor. But equivalently, I have a point in the face here. Another point in this face. In fact, I can consider, once again, like I did before, the basal plane here, the xy plane. And how many red points do I have in that plane? 4. What about the xz plane? 4. YZ, 4. Right? So in each plane, I will be able to identify 4 points along the diagonals. So it's a total of 12. So FCC has 12 first nearest neighbors, and they are located at square root 2 over 2A. Now you might remember now the sequence. Simple cubic was 6, BCC is 8, and FCC is 12. 12 is the maximum I can accommodate. You remember the discussion we made last time about spheres, packing of spheres. If I try to pack spheres, I can at most pack 12 spheres around myself.
So we have the same number for hexagonal.
Yeah, HCP would be the same, 12 nearest neighbors, yes, correct. As well as any of these different arrangements of stacking of layers in our discussion we had A, B, C, B, B, and so on and so forth, okay? In all these arrangements, you are going to have 12 nearest neighbors. Second nearest neighbors for the FCC, where are the second nearest neighbors now? Where do I go if I look for the second nearest neighbors? At distance A, sorry, yes, distance A. So I'm using green, I guess, yes. Right, how many do I have? 6. So 6 second nearest neighbors at distance A. Right? Okay. Any question regarding nearest neighbors? Good. Yes?
The nearest neighbors, the same as the coordination number.
Yeah, sorry, yes. Some people call it coordination number, you're right. Coordination number. Sure, correct. All right, now we change a little bit the discussion, and I would like to mention a few, briefly, a few experimental methods that allowed us to understand the structure of crystals. I mean, how do we know that crystals are arranged in that way? Atoms are located at the distance of a few angstroms from one another, and certainly we cannot use our eyes to determine whether something is a crystal or not. I mean, we need to use some sophisticated experimental tools to determine whether a system is arranged in a crystal structure, or in general, what is the local arrangement of atoms in a given structure. I mean, how do we know this from experiments? Now, there is, of course, an enormous variety of probes, experimental probes, to determine the location of atoms in a structure, in a crystal or in a more disordered structure. I'm just going to mention a few just because they are the most common. So it's just going to be a very limited and quick discussion about experimental methods. Probably say, the most visually obvious is a method that's been developed not so many years ago, about 20 years ago. And this is really a method that allowed us to really get the first real pictures, real pictures of what the atoms look like and how they arrange themselves in a crystal. And this was thanks to a development that was made in the mid-80s that goes under the name of scanning tunneling microscope. STM. What is an STM? The STM is a system, essentially is a way to probe a material by, if you have a material here, by coming close to a material with a metallic tip. So you have a tip made of metal. And that's your probe. This is your sample. And if you're able to make the tip sharp enough, eventually the tip will be terminating, of course, with an atomic structure which is rather sharp, hopefully. I mean, if you are good enough at preparing these tips, you can generate these tips in such a way that the tip of this object is really, made of a few atoms. Now, if you come closer with your metal tip to your sample, and you apply a voltage between the sample and your metal tip, you can expect at some point that there will be current flowing in either direction, depending on what is the voltage, of course, either from the sample to the tip or from the tip to the sample, depending on the voltage. Of course, this requires that the sample is also metallic, because otherwise you won't have any conduction inside the sample. There are tricks that allow you to avoid this, but to first approximation, this requires you to work with the metal as well. So you can only study metals to first approximation with this method. Now, what's the beauty of this method? There's going to be, here you have vacuum, right, between the tip and the metal. So in principle, electrons are unable to jump from one system to another one if there is a vacuum in between. They do it, however, if you bring your tip close enough to the sample, and they do it through a tunneling effect. I'm sure you've seen the tunnel effect in quantum mechanics, right? If you have a barrier which is small enough, say, at the angstrom, of the size of a few angstroms, then you can expect that the decay of the wave function on the two sides of the barrier is such that there is an overlap, and therefore that you have a finite current that can flow from one system to the other one. So you have to be able to bring your tip at a distance of a few angstroms from the sample. But if you manage to control your tip, notice this is from a practical point of view is a challenge, because you need to align a tip, so an object that is distinct from your sample, and you want to align it with a precision of a few angstroms. That's very difficult from a practical point of view, because these are two macroscopic independent objects that you want to align with a precision of an angstrom, so a few angstroms. But suppose you manage to do that. At that point, you will start seeing electrons tunneling. You won't see anything at the beginning once the tip approaches, because there's a vacuum in between, there's no current. So these two systems remain charged according to the voltage that you give. At some point, you will start seeing a little bit of current flowing, and that current is the tunneling current that flows through the vacuum thickness. As soon as the distance, the barrier between the tip and the metal is short enough, of the order of a few angstroms. Now, the interesting point now is that this current has an exponential behavior, because it's the overlap between the exponential tails of the wave function. So if you consider the current from a three-dimensional perspective, you will have electrons coming from all places in the metal. Clearly, this distance is going to contribute to the current only for an area which is also of angstrom size, right? Because electron from here will have a huge distance to tunnel through if they want to go to the tip, all right? So the point is that if you come close enough with your metal tip, you're going to extract electrons only from a region of space which is of comparable size to the distance between the tip and the sample. Now, suppose you now move your tip horizontally, like this. Let me now expand it here. And then these are atoms. This is an atom with the charge distribution. This is another atom with the charge distribution. Another atom with its charge distribution. And then what I'm plotting here is, for example, the profile of constant density that you see on top of the corrugation, the density corrugation on top of a crystal. So this will be of the order of angstroms. Distances of the order of angstroms, heights here of the order of less than an angstrom or something like that. And you're able with your tip to move it horizontally like this. Very, precisely controlled. If you're here, you will have current flowing from points located here, here, and here, so at a given distance from the sample. If your tip is here, the distance, the barrier, will be much shorter. So your current will be exponentially higher than it was when you were here. So if you now record your current as a function of position, you will see huge oscillations in your current. In other ways, you'll be able to map the local topology of your sample. In other words, you'll be able to see a picture, to make a picture, to take a snapshot of the surface of a material. Now, this is a technique that has really revolutionized, in general, the field of, the understanding of the structural properties of solids, because it was really the first time that scientists could take a picture of the structure of a system. You could really see atoms one by one and measure precisely the distances between the atoms visually. Of course, not visually with your eyes, but visually on your screen when you were analyzing these oscillations of the current as a function of the position. Of course, all this required an enormous effort to be able to control, once again, the position of the tip in a very precise way on top of your sample, which, by the way, means that you have to completely remove all possible vibrations from your system. So you have to do experiments in a setup which is completely isolated from vibrations due to the environment. In fact, the first experiments used to be done during the night because there was, of course, less noise and less vibrations. In fact, the story goes that in order to isolate the system from vibrations, they placed tennis balls below the table. They put a table on top of a number of tennis balls in order to isolate it from vibrations from the ground, coming from the ground. And all this was also made available because of the use of very precise piezoelectric materials. So they were controlling the position of the tip using piezoelectric materials. Piezoelectric materials are materials that allow you, by change of voltage, they can expand or contract, okay, by very small amounts at the angstrom level, by applying a small voltage. Yes?
Using this method, you've done only...
Correct. That's the very good, exactly, that's the next point. This only allows, unfortunately, to look at structures of surfaces. There's no way you can look at the inside of a material with this method. That means that what you see is just the surface, and the surface may not be very representative of the bulk. There might be atoms at surfaces might be taking different positions with respect to atoms in the bulk. I would say the periodicity here is likely to be the same. There's no reason why the periodicity in the plane should be different with respect to the periodicity in the bulk, but certainly you won't be able to obtain any information about the periodicity in this direction, for example. So this is an extremely nice and beautiful method to visualize structures of solids. However, it only allows you to detect the structure of the surface. Okay? But you may have, for example, molecules on top of the surface, right? You can deposit, for example, a CO molecule on top of the surface, right? Then you would see a charge density due to the molecule. And with your tip, if you go here, you will see suddenly a jump in the in the current due to the fact that you're heating a molecule, right? So you'll see the shape of the molecule by looking at the change in current as a function of position, lateral position here. So people were really able to also to map, to look at molecules on top of surfaces, determine the size of molecules with this method. This, by the way, gave the Nobel Prize to the inventors of the method, Binnig and Röhrer. It was in '84. Discovery was made in '83. Okay, so this is, I mentioned this method first, although historically it's probably the latest one, because it's the one that probably gives the most beautiful results. You really see pictures of atoms arrange themselves in a solid. Let me now briefly discuss other methods that are more indirect, less obvious. You need to interpret the data in order to understand the structures. Another very, old and much older than STM method to determine, yes?
Can we tell using this STM the density of electrons?
You can also determine the density of electrons, yes. There is a whole theory behind it. Unfortunately, the course is too short to discuss the theory of this, but if you wish, I can give you references about the theory of the STM. And yes, this method can only also allows you to determine not only where the atoms are, but what is the charge density, what is the electron density.
Yeah, because if we have on the surface high density of electrons, then the profile that we are going to see will not be like, will not change. I don't know.
Too much, you mean? The corrugation would be...
If we have high density of electrons on the surface,
yes?
then this one works in principle as the flow of electrons, right?
Mm-hmm.
So we have like a constant flow of electrons since we have many electrons on the surface.
Okay, so your question is, if you have a large density of electrons here, is your current is also going to be large, of course. But what we're interested in is variation of the charge density, not really absolute value. So I guess, it's not really going to change too much the results. Yeah, there's a whole theory. There's a whole, thousands of papers, books about it. So if you wish, I can give you references about this. So other methods. The second, indirect methods can be, generally speaking, classified into two main categories. Local methods and diffraction methods. We're going to spend some time on this in a moment, but let me discuss briefly the local methods. What do I mean by that? By local methods, I mean methods where you essentially look at the properties of a single atom, and you look at how much the properties of a single atom are modified due to the presence of an environment. Okay? They're called local because in this way we understand what is the local coordination, the coordination number of an atom in a crystal, but we may not be able, with local methods, to tell whether a system is crystalline or amorphous, for example, because we don't have the big picture. We only see locally the nearest neighbors. So we won't be able to tell whether there is a long-range order, an ordered crystalline arrangement. Vice versa, diffraction method, you're probably already familiar with that, but we're going to discuss them quite extensively in a minute, will give you a big picture. Will tell you whether the system is ordered, and if it is ordered, what kind of order you have, what kind of crystal structure you have in your system. Okay? Let me just give you one example of a local method, just one, because there are so many. Probably the oldest one. The oldest one is based essentially on X-ray photoemission. Spectroscopy. So people now currently refer to it as XPS. In the past, it was also referred to as ESCA, electronic spectroscopy for chemical analysis, I think. So it's electronic spectroscopy for chemical analysis. This is also Nobel Prize, 80s, I think. What is the principle? The principle is the following. You have an atom. So now I'm reporting the energy. Suppose you take a given oxygen, for example, right? Oxygen will have some energy levels with some wave functions, right? This is not, of course, the real representation of the oxygen wave function, but just schematically representing here the wave functions of the oxygen atom, right? So you may have the 1s state, the 2s state, the 2p state, 3s, and so on and so forth. Now, for oxygen, which ones will you fill? And this, right? You have 8 electrons in oxygen. So you will place 2 electrons here, 2 electrons here. You can place 6 electrons here, but you only have 4 more available, right? So I'm going to place 4 electrons here. And out of these 2p states will remain empty, essentially. And this is empty. Now, the position of the 1s state is going to be very deep in energy, because this is a core state, right? It's the lowest lying state. And for oxygen, it lies at, I guess, something of the order of 500 electron volts. Okay, so it's very deep in energy with respect to the vacuum level. This is very deep. It's the lowest lying state, the 1s state, and it's very deep in energy. And it's essentially, the wave function is very localized. 1s electrons are very, very close to the nucleus. We'll come back to this, by the way, later on when we discuss chemical bonds. But what I wanted to discuss now is a simple effect, and it's probably the simple consequence of placing close to the oxygen atom other atoms. For example, oxygen is a very good example, because oxygen likes to accept electrons from other atoms, right? It can change the oxidation state very quickly, very easily. You can take -1, -2. -2 is probably the most common oxidation state for oxygen. So oxygen likes to acquire 2 more electrons to fill the 2p shell, right? Oxygen 2- is a very stable ion. So it can accept 1 electron or 2 electrons, or even sometimes even more than that, depending on the chemical environment. If you if you put oxygen in the proximity of a system that likes to donate electrons, then oxygen will accept those electrons quickly. Okay. I don't want to discuss now the details of how this happens, why this happens. I just want to discuss the consequences of this. You have electrons, the number of electrons in oxygen changes, because there's going to be more electrons on the 2p level, 1 or 2. Suppose it's 2, for example, oxygen 2-. At the same time, the atom that is close by, perhaps you have atoms both to the left and to the right side, actually surrounding oxygen, are going to be depleted of electrons, because these electrons have to go to the oxygen, right? So if you sit on your atom here, and if you are your 1s electron, you will see some positive charge here, some positive charge here, and some additional negative charge here, actually 2 electrons here. So clearly, the electrostatic potential that I see if I'm a 1s electron is going to change dramatically with respect to the electrostatic potential I would see if I was oxygen, pure oxygen, without any additional charge. For 2 reasons. One, because I have 2 more electrons on top of myself, right? And also because I have positive charges surrounding myself, typically in the nearest neighbors, in the range of nearest neighbors. All right? So the position of the electrostatic potential of this 1s state depends heavily on the charge state on the valence state of the oxygen itself. also on the position, distance, and charge state of the nearest neighbors. And the changes due to this electron transfers can be of the order of 2-3 electron volts. Of course, this is very small compared to the binding energy of the 1s state, but it's still, not negligible. So this state will go up and down just because the electrostatic potential here at this point is affected, is changed by the fact that you have charge transfer, or because you have some positive charge outside. So it's very sensitive, the position of the electrostatic potential is very sensitive on the charge state of your atom, but also on the position and charge state of your neighbors. At this point, you can think of doing experiments in which, with a photon, you take this electron out and you bring it to outside your sample. And you can measure this energy, the binding energy, because you can take a photon with an energy possibly higher than the one required to ionize the system, the minimum one requires to ionize the system. And this energy here is entirely going for this electron into kinetic energy, right? If you take an electron from here and you bring it here, this is the energy required to take it out of the system with zero energy outside, and all the rest is kinetic energy, okay? Kinetic energy of the electron. So if you have a photon with a given energy and you measure the kinetic energy of the electron that you are extracting out of the system, and you can do it very easily. You can easily measure the kinetic energy of electrons coming out of your sample. Just use, for example, a magnetic field, and you look at the radius of deflection in a magnetic field, for example. So it's very easy to measure the kinetic energy of an electron emitted in a vacuum, the vacuum. You measure the kinetic energy, you know the energy of the photon that you use to extract this electron. What remains is the binding energy of the electron. Okay? And depending on your result, you can then study the environment of your system, of your atom in the crystal. The oxidation state, for example. Of course, to do that, you require photons in the kilo-electron volt range. Okay? So these are X-ray photons, typically. That's why this is called X-ray. So here we explain all the words, right? X-rays, because I need an X-ray photon to excite an electron out of the system. Photoemission, because I'm emitting the electron with a photon out of the sample. Spectroscopy, because I measure the kinetic energy, and by that I can extract the binding energy of the state, of the initial state, of the core state. Or, in the old terminology, this is spectroscopy of electrons, photoemitted, of course, for chemical analysis, because in this way we understand the chemical state of the atom. The synchrotron facility here in Trieste, you know that there is an experimental facility in the half-an-hour drive from here, a big one. It's a facility which is dedicated primarily to this kind of experiments, because it's a facility that produces X-rays, and therefore X-rays are there used for a number of different experiments, including X-ray photoemission spectroscopy, for example. The energy of the photon that you send on your sample. Okay? So you send the photon with this energy. So h bar omega is the energy of this photon here. This energy must be larger than the binding energy, because otherwise there wouldn't be enough energy to extract the electron out of the system. The electron will remain inside the sample, inside the and it will decay back to the original state eventually. But if you manage to have a photon energy which is larger than the binding energy, then the electron will be emitted away from the sample with whatever kinetic energy remains. And that the kinetic energy that remains is the difference between the photon energy, the energy that the electron has acquired by absorbing the photon, and the energy required to take the electron out, which is the binding energy. Whatever remains goes into kinetic energy outside. Okay? It's like taking an object out of a wall. You have to first pay the cost of gravitational energy to take the object from the bottom of the well up to the surface, and then after, if you give additional energy, then this object will move away with the kinetic energy equal to the excess energy that you provide on top of the gravitational energy required to take the object from the bottom to the well to the surface of the well. Okay, and you can measure this. You know the photon energy because you shine light with a given frequency. Okay, in your experiments, the difference is the binding energy.
Is this energy the same for all the layers?
For all what?
Layer.
For all the layers of what?
Yes, because we have the state 1s, 2s.
No. Well, if you want to observe electrons in 2s states and use the same photon energy, okay, that's a good point. Suppose you shine light with the same photon energy, fixed. Let's use real numbers. Suppose that this is 500 electron volts, okay? And I choose a photon of 600 electron volts. Okay, so the energy of this photon is 600 electron volts. Electrons that were originally here will be emitted with a kinetic energy of 100 electron volts, right? Okay, so I will have electrons moving away from the sample with a kinetic energy of 100 electron volts, because 500 electron volts are being used to extract the electron out of this state, and the remaining energy will go into kinetic energy. If, however, the photon is absorbed by the 2s state, well, this electron will then be emitted up 600 electron volts above this level. And because the binding energy of the 2s state is 40, 30 electron volts, the 2s state participates, it's a valence state, it participates in chemistry, so it's very close to the vacuum level, 2s state. So this is probably 20, 30 electron volts. 600 electron volts, that brings me kinetic energy of 500 and more electron volts. So the electrons, when I look at my kinetic energies and I shine my sample with 600 electron volts, I will see two classes of electrons. I will see slow electrons coming from the 1s states, and I will see very fast electrons coming from the 2s states, the 2p states, at much higher kinetic energy, because the cost of extracting them out of the system is much less.
It's like a photoelectric effect.
It is a photoelectric effect. It is. Photo emission is the photoelectric effect, essentially. Correct. Okay? We are going to discuss in more depth these electronic states later on. I'm just giving you a quick flash of these concepts now. We're going to come back to these concepts later on when we discuss the electronic structure. And again, this is just one of the zillions many different ways to probe the local structure. There are more sophisticated tools nowadays that are all more or less based on the same principle. You try to extract electrons out of core states, and by doing that, you learn something about the local environment. You'll never be able to know here whether there is an ordered array of atoms in these systems. You'll only be able to learn that there are two positive ions close by, and that the part of the charge that was here is now on the oxygen. You won't be able to learn anything else about the remaining part of the sample of the crystal. So that's why these are called local probes. Okay. 10 o'clock. Let me now spend some time. In fact, we're going to spend probably this lecture and the entire lecture of Friday on diffraction methods. Yep.
We can only have two positive ions or more.
You mean here? Well, I mean, yes, we might be able to understand also whether we have 2 or 4 or 6. I mean, we might be able to understand whether there are 6, 8, or 12 positive ions surrounding my atom, right? What would you be able to argue then? That your crystal is simple cubic or BCC or FCC, for example, right?
What is in this case, what structure?
Oh, sorry, no, that was a one-dimensional. Sorry, it's just, of course, we're talking in 3 dimensions, so it's 6 probably, or 8 or 12, I don't know. Just an example, I mean, just to show you that you can understand something close by. 2 doesn't exist, of course. It's a one-dimensional object, yeah. No, but just to tell you that, I mean, based on this shift, you might be able to understand whether you have, for example, the number of nearest neighbors. And from that, you may, suppose you find 12, for example, then, okay, you know that it's not BCC, it's not simple cubic. It must be FCC, HCP, or some other structure. If it is a crystal that you will never be able to tell based on these experiments, it might be an amorphous system, you don't know.
How are we going to find this number? The number of
Nearest neighbors? Well, it's based on, of course, on accumulated knowledge. You need to have information about how much this position of this binding energy changes due to the presence of nearest neighbors. Okay? So it's I mean, it's not something that you can easily predict, but if you find a given change in a material that you know has 4 nearest neighbors, and you take another material with 6 nearest neighbors, and you find that the binding energy is different, next time you do an experiment, you measure the binding energy, you compare whether it's closer to the 4 one or to the 6 one. And you say, okay, it's closer to the 4, must be 4 nearest neighbors. Okay? It's based on, of course, on some previous knowledge about changes in the binding energy as a function of the local configuration. It's not something that you can immediately tell what is, how much these energies change as a function of the nearest neighbors. But it is, I mean, a parameter that certainly changes due to the local environment. That's the main point of this story. How you then correlate precisely this change to the local environment is a very difficult it's a very difficult exercise that requires you to know examples for which the structure is known and to know how the binding energy changes in structures that are known.
are these energies tabulated or?
Yeah, they're tabulated, yeah. For oxygen, for example, you can find tabulated all the different valence states. Okay, they're tabulated in most chemistry books. You'll find it tabulated. All right. Let's talk about diffraction now. I think I need more space. Can I? Are you all fine with this? Now, let's assume now that we have yes.
Using this method, we can only tell about certain methods, like okay, certain materials. I think, like if the binding energy is in the order of some electron volt, which is less than the energy of X-ray. Is that right?
Yes. So your question is whether with this method we can understand the properties only of some classes of materials, which is where the binding energy is small with respect to the change in the binding energy is small with respect to the value of the overall binding energy. Is this your question?
Okay. The energy of the X-ray is in the order of.
The energy of the X, I mean, you can have very different values for the binding energy of core states, right? Oxygen 500 is, I actually forget what it's 500, it's close to 500. Is on the lower side of the spectrum. If you take heavier elements, the binding energies can be much larger, of the order of several kilo electron volts for heavier elements, of course. Let's say the crucial parameter here is how much is the change in the binding, not really the value of the binding energy, because you can find an X-ray, some source of X-rays for that particular binding energy. The point is really how much is the binding energy changing with respect to, as a function of the local environment, because you need to be able to measure a few electron volts out of 1,000 electron volts of photon energy, right? So your technique must have a very good resolution in order to be able to detect, of 10 to the minus 3 in this particular case, in order to be able to detect 1 electron volt. Now, binding energies, changes in the binding energies can be small, unfortunately. They don't necessarily need to be large. They're typically large when you have charge electron transfer, so charge transfer between, so if you have a change in valence state, formation of an ionic system, for example, then the change is typical of the order of electron volts. If you're in a metal, for example, changes in the binding energies due to changing coordination from 8 to 12, for example, in a metal, can be very small, can be of the order of 0.1, 0.2 electron volts. And therefore, your accuracy in measuring the photon energy and in measuring the energy of the kinetic energy of the electrons must be very good. So that's really the crucial point that you want to achieve in an experiment. You want to be able to measure these changes with an accuracy which is sufficient to allow you to make statements.
Why we choose only X-ray?
It's only X-rays. The question is why it's only X-rays. It's only X-rays because you want to look at core states. And the core states, as soon as you go beyond oxygen, let's say, 1s state goes deeper and deeper, right? So you're talking about kilo electron volts. And you want core states because core states are very localized in space. And so you can easily understand the electrostatics of a core state because it's a point charge. It's like having a point charge. As soon as you go to valence states, the charge distribution is large. And therefore, considerations about electrostatics might become a little bit more complex, right? So you want to work with X-rays in order to probe the core states. Also, the core states are the ones that are not affected by chemistry. You want to somehow remove chemistry here. You want to understand chemistry only through changes in electrostatics. If you start talking about valence states, you're going to also be affected by the chemistry. And that, of course, adds an additional complication to the problem. Yes?
One thing I never understood before.
Mm-hmm.
If the energy of the photon is exactly equal to the bound energy.
Okay, so if the energy of the photon is exactly equal to the binding energy,
Okay.
then?
Do the electron extracted?
Okay, what do the electrons do in that case? In that case, the electrons will be brought exactly at the vacuum energy, at the energy of the vacuum, and therefore, well, will probably stay there, but otherwise, if they're able to exit, outside the sample, they will exit with zero energy, okay? Right? Because you have given enough energy to the particle to get from the bottom of the well up to the surface. And you're there, you're right at the surface, so the electron will not move, will not do anything, because there's no additional energy to do anything.
In this case, is electron stable or?
Well, it depends, but presumably if you're too close to that value, the electron will just decay back to the core state without and not being emitted, right? There's not enough energy to be emitted, so it just recombines down to the... Also, you have to think that you are exciting an electron, but this electron has to be able to escape outside the sample. So if you're exciting this electron deep inside the sample, it has to be able to reach the surface and then be emitted. So if you're really close to the edge, probably the scattering will prevent the electron from being emitted outside the sample. So you don't want to be really close to the threshold. You want to be much above the threshold in order to be able to measure your kinetic energy properly.
Okay. What if a second electron moves near this electron?
What if a second electron moves,
Yes.
coming from where?
From other metal, for example. We put a second
You want to put a second metal close to the sample and have and also photo-emitting electrons from the other metal, or what? Or these are just electrons in the metal?
No, we have electrons at the surface,
Mm-hmm.
and we put close
Right.
another metal, and in this metal there is an electron which is moving
Away.
yes.
Okay, so the question is whether if you take if you photo-emit an electron from one system, and then you have close by another metal with other electrons, okay? Well, these electrons will be, I mean, the electrons in the second metal will be bound inside the material because you have to pay an energy to extract the electrons out of material. You have to pay work function, an energy equal to the work function to extract electrons out of a metal. So I don't really see the connection here. How much could the presence of an additional metal affect the emission of an electron from your sample?
Okay. Can this affect, can we, in this case, attract this electron which is...
The one that is emitted or the one in the second sample? In the
one which is
okay, the question therefore is, can we facilitate the extraction of that electron by putting close to the sample another metal? I don't really see the advantage of doing that because the electrons in the second metal will be confined inside that system because their energies are at least below the work function, right? So there's nothing, I mean, these electrons are stable, they're there, and the system is a metal, is neutral. I don't really see how this could facilitate the extraction of an electron from the other system.
What if this electron was moving in the vacuum?
Which one? Oh, another electron moving. You're increasing the complexity of the experiment to the point that I'm unable to predict what's going to happen. I mean, you're adding too many things. I mean, I don't know. People might have looked at photoemission spectroscopy in the presence of additional electrons, but it looks like a very odd kind of experiment. If you were able to come up with predictions, I would be pleased to know what you predict. But it looks like a complex experiment, and it's.
In this metal, we can extract the electron.
Okay, you want to facilitate the extraction of an electron using other electrons. I don't see the point because you just need to increase the photon energy of your light to extract electrons. So why do you need to complicate your life? And okay, it's getting too complicated. It's not that you pay for your energy. It's not that a photon of 500 electron volts costs you more than 600 electron volts. It just depends on your source, and your sources are, if you use a synchrotron facility, you can essentially tune actually, it's easier to get photons with larger energy than photons with lower energy at the synchrotron facility. I need to continue, otherwise, we can discuss later on about this, okay? Okay, so we have a sample here, a macroscopic sample. And we have a crystal. We don't know it yet, but we know it's a crystal. Well, we don't know which crystal. We perhaps know it's a crystal. I'm now magnifying everything, right, in order to make it visible. So we have an ordered array of atoms inside my crystal, in grains or whatever. And what I'm doing now is I'm shining light, okay, with a given frequency, given photon energy. This light here will have also a momentum, okay. You probably know that the two are related, the frequency and... Are you familiar with this, I hope? Okay, so omega over c is equal to the momentum of the photon. What this means in practice is that you have an electromagnetic wave, epsilon, which I call incoming, which is some polarization vector times e to the I k dot r minus omega t. we put in here to distinguish the out vector. Okay? This is the electromagnetic wave. I hope you're familiar with this, right? You took a course in electromagnetism, so I'm sure you're familiar with the concept of electromagnetic waves. This is an electromagnetic wave which is propagating in the direction of k in, momentum k in, and the frequency is related to the momentum in this way. It's a free electromagnetic wave. And this is coming, I'm shining light onto my sample. Then what I do, I position myself here, so these are my eyes, and I look at the electromagnetic field that is coming out of the sample. I'm not positioning myself here, by the way, because otherwise I will probably be blinded by the incoming light, right? But the light that is not absorbed or scattered by the material. So I don't like to position myself here. I like to position myself somewhere off the direction of k in. And I look at the electromagnetic radiation, which is emitted in this direction from the sample. So that will be light emitted with momentum k out. So it will be some polarization times e to the I k out minus omega t. Now there is certainly something that I can say about the values of k out and omega. If light has a given frequency, it will, for example, hit this atom. The charge density of this atom will start oscillating as a consequence of the electromagnetic field, incoming one, with a given frequency, which is the same as the one of the incoming electromagnetic field. And because this charge is oscillating, it will emit radiation at the same frequency, of course. And this is precisely what I'm seeing when I put myself far from the sample at a given direction. I'm seeing the electromagnetic radiation generated by the charge density of the sample as a consequence of the fact that it was excited by the incoming field. So there's certainly something I can say for sure, and this is that this omega here is the same as this one. Right? Coming light, the electrons are oscillating at the same frequency, of course, and they're emitting light at the same frequency. So certainly I can say that this omega is the same as the incoming one. Obviously, because of this relationship, I can also say that k out being equal to omega c, omega over c, will have the same length, absolute value, than k in. It will be in a different direction, but it will have the same absolute value, k out, the same absolute value as k in, well, the same length, because omega is the same. So I fixed a number of things here in my expression, and I related them to the incoming field. Let me now discuss a little bit more about phases. What is the phase of this field here with respect to the phase of the incoming field? Now, to do that, I need to focus myself on a given atom. So let me call this Ri. So this is the position of atom I. So this is atom I in the system. I have an a very large number of atoms, which I label with numbers. I have atom I here, and that atom I will be positioned at position capital R of I. Okay? So here, in this particular position, the value of the electric field will be given by, of the incoming electric field, will be given by, at this position here, I'll write it here, e to the I k in dot Ri minus omega t, obviously. Right? I mean, of course, forgetting about the polarization, which is fixed. But if I'm at this position, I just need to place myself here, that is putting capital R as the position in my electric field, and I can tell you, well, the value of the electromagnetic field as a function of time here will be given by this term in that particular place. Now, at this point, I'm starting to emit my light. So the emitted light will have to travel from here to my point far away in space. So if I'm positioned at point capital R, actually let me call it observer, just to distinguish it from the other ones. The phase with respect to this point of the outgoing field, notice, with respect to this point, I want to now understand what is the phase of the electromagnetic field here, of the outgoing one, with respect to the phase the outgoing field has here. Now, this is essentially given by this term, right? If I position myself in a different place, I simply need to evaluate e to the I k out dot R observer minus R I. Right? So this is the phase, let me say it again, this is the phase acquired by outgoing field, electromagnetic field, from Ri, the position where it was emitted, to observer. Right? Do we all agree with this? If I go from here to here, the phase will differ by this amount, the phase of the outgoing field. Just the difference of the electromagnetic field at a given time between here and here. But the phase of the outgoing field here is determined by the incoming field, right? Because my electrons will oscillate as a function of my incoming field. So the overall phase of the electromagnetic field at this position will be the product of the original phase of the electromagnetic field here, which is given by the incoming field, times the phase acquired by the outgoing field going from here to here. Ri minus omega t times e to the I k out R observer minus Ri. Right? So if I want to know what is the phase of the electromagnetic field here, due to atom I, mind you, due to atom I, this is going to be given by the phase of the incoming field at the position of atom I. This electromagnetic field will oscillate, will generate an outgoing field, and then what I need to do is to just measure the phase, calculate the phase of the outgoing field from atom I to the observer. So the overall phase of the electromagnetic field here, due to the emission of atom I, will be given by this expression. Let me now group the terms a little bit. So I'll have a term which is independent of the atom, and it's this one, right? This term here does not depend on the atom. And then there's a term that depends explicitly on the position of the atom that I considered in my emission. I've just regrouped the terms here, right? I've grouped them in a factor which is independent of the atom I, and the term that explicitly depends on the position of atom I. Yep.
In general, K out is not a single number, right?
What do you mean a simple number?
It depends on the structure and.
I mean, I didn't put any constraint here. I just set myself somewhere around my sample. Okay, I know for sure that the length of K out must be identical to the length of K in. So if I come in with a given light, I can only see light at K with this constraint. And then I didn't say anything else. I just said I position myself arbitrarily around my system. So what I can play with, of course, is with the direction of K out. And so far, I have put no constraint on the direction yet. So this is general. What I need to consider now, before I move forward, is the fact that this is not the only atom that is emitting light. There's going to be this one, this one, this one, this one, all of them, right? And their contribution is going to sum up in the final signal that I see here. So in principle, I need to sum all these phases over all the atoms in my crystal, right? Atoms. Now, this is independent of the position of the atom. So I can forget about that. I can just take it out of the sum. It's going to be an additional factor on top of all the other ones that I didn't consider. The interesting one, of course, is this one, because this one really depends explicitly on the position of the atoms. So when I do the sum, I have to be careful. So what I need to focus now is on this contribution, this term here. K in minus K out dot Ri. With the constraint that K in and K out have the same length. That I have to remember. K out here. Okay? So I hope the physics is clear. Incoming electromagnetic field, charge is oscillating, same frequency. I add the phase it takes for the electromagnetic field emitted by this atom here. Where is it? Here. And I get an expression which, I mean, in addition to constants which are irrelevant for me, contains the sum over all the atoms of the phases of the electromagnetic field emitted and that I'm going to see as a function of the positions. This is the interesting part, because remember, my goal here is to use this. Sorry, I should have said this at the beginning. My goal is to use this to be able to tell what is the structure of the system. So I need to find something that is going to tell me where the atoms are. So out of all this, I'm going to extract the part that depends explicitly on the positions of the atoms in my system. Yes?
I just want to go back like this to show me, okay, this equation for which, and then the first one, I want to see the difference between the.
No, I'm saying this one was our argument until this point was based on the emission of a single atom, as if all the rest didn't exist, as if we had only this atom in the whole system, period. What I'm doing now is I'm assuming that I have many atoms, not just one, and each one of them is emitting light, okay, in the same way. I could have considered this atom or this atom. Yeah? The only difference would have been the position, which is different, right? Ri. So now I'm going to sum over all of them, because each one is emitting light, is emitting electromagnetic field, and if I sit here and I observe the field, what I see is the sum, the superposition of all the electromagnetic fields emitted by all the atoms. So I need to sum all of them. And what I do here is just remove portions of the expressions that don't depend explicitly on the positions. They're going to be the same regardless of what sample I have. That only depends on the geometry of the experiment. This is really the most crucial part, because this is really going to tell me, to give me information about where the atoms are. Yep.
We have free electrons on our sample.
Yep.
The electrons may absorb the incoming ray and
All right. So your question is, yes. Suppose I have free electrons and not electrons bound in an atom. What do I do with that? Well, the theory is a bit more complex, and therefore I need to use this approximation, which is not really an approximation, because if you look at the charge density in a solid, it is, in fact, primarily made of a superposition of atomic charges. You can, of course, describe it also in terms of free electrons in some cases, and we'll see examples of that. But we are not that far from the truth when we say that the electronic charge is primarily given by the sum of the atomic charges contributed by all the atoms. But you're right. I mean, this theory assumes that the atoms are all independent and the charge densities are independent. What if there is correlation between the electronic states in atom here and atom here and so on and so forth, to the limit, for example, and what if we go to the extreme limit of free electrons? Free electrons don't even know that there is an underlying crystal, right? In fact, if you push that to the limit and you say that your electrons in this system are all free electrons, are only free electrons don't know that there is an underlying lattice. So you'll never be able to extract information with X-ray diffraction, because the electrons will not tell you anything about what's below them, about where the nuclei are.
yeah, but they can emit radiation. That can.
Yes, but you won't be seeing any diffraction, because they will not carry information about the underlying lattice, right? So the extreme case of a free electron is a good one, because it's an example where no way you will not be able to extract the information about the nuclei, because the electrons don't even know about the existence of a regular lattice. So you need to somehow go in the direction of assuming that there is some structure and there are atomic charges. Otherwise, you won't be able to extract any information from the system. Yes?
Okay, we don't see all the electrons with the same angle.
But okay, good point. So the question is that you don't see all the atoms from the same angle, right? The angle here is here, and the angle is like this. Okay, I didn't mention it, but there's another approximation that we're making, is that this observer is far enough in space that K out is the same for all the atoms. Correct, thank you. So we're assuming that the dimensions of our sample are small enough and that our detector is far enough from the sample that the difference between different K outs is negligible. Correct, thank you. Okay, so I'm going to now focus on this expression now. Now, this is a sum. If I fix my detector position and I fix my light, this object is fixed. It's a sum vector. So then the question is, what is this sum going to, what is it going to give me if I sum it over 10 to the 23rd atoms, right? Because I have a macroscopic sample, so here I have something of 10 to the 20, 21, 22, 23rd. So I'm going to make some phases out of a huge number of positions. Now, these phases are going to add up in a complicated way, of course. And in principle, I mean, if these positions were really random positions, we are not dealing with a crystal now, we're dealing with random positions, this phase is going to be a random number. And if I add up random phases, what do I get? if I take this exponential, which is cosine plus I sine, and I take random phases, so cosine of theta, average over random values of theta, what does it give you? Cosine is an oscillating function, right? It takes positive, negative values. If you sample it at random, what do you get? 0, right? So same for the exponential. E to the I something, if this thing is random, you're going to get 0. No signal. So if you're an amorphous, by the way, and you try to look at this, you're most likely going to see nothing. Because all these phases add up in a random way, and the final result is nothing. Okay? Well, it's not really nothing. It's nothing if you sum up over real random numbers and if you're summing up over an infinite number of them. We have a finite number of atoms, and even in an amorphous, they're not really randomly positioned. There are some constraints, like the distances between atoms have to be more or less the chemical ones, and so on and so forth. So the bottom line is that even for an amorphous system, the signal is not exactly 0. It is finite, and you can extract information about an amorphous system out of these experiments. But clearly, there is a case, if we manage to find it, and we are in a crystal, for which you can maximize this sum. Well, one is obvious, right? If k in minus k out is 0, obviously this is 1, and there I'm summing ones, and that's actually the maximum I can achieve, right? If I sum all the phases equal to 1, here I'm going to get the total number of atoms. So that's really a way to maximize my signal. But of course, k in minus k out equals to k0 means that k out is in the direction of the incoming beam. And also, if I make k in minus k out equals to 0, I lose all information about Ris. I will get 1 whatever is the structure. So I'm not going to learn anything about the structure. I'm just going to maximize the signal, but I'm not going to learn anything. Is there any way to make this thing maximum for finite values of this? So let me now ask a very important question from a mathematical point of view. And those of you who are familiar with the reciprocal lattice will now, something will click in your mind. If you're not familiar with reciprocal lattice, you'll learn it. But if you're familiar with reciprocal lattice, I'm sure that there will be something click in your brain at this point. So let me now assume that Ri is a crystal that I don't know yet, but it is a Bravais lattice, for example. Okay, so I'm assuming that the Ri's are all points of a Bravais lattice that I want to determine. Question: can I make this object equal to 1 for all Ri's? Wow. I have a 10 to the 23rd Ri's. Of course, I know that if this is 0, I can make it 1, obviously, but that doesn't give me any information. Is there any other choice of this difference that makes this equal to 1 for all points in a Bravais lattice? So can I find a vector G? I'm simplifying the notation simply. So I'm calling this difference G. Such that this is 1 for every value of the position of the atoms in a Bravais lattice. That, if I'm lucky enough to find it, notice this has to be true for every value, an infinite number in principle of points. Can I find a vector, single vector, that gives me 1 for all positions? If I'm lucky enough to find it, right, then I make this one for all the Ris, and this signal is again going to be huge. I'm going to have a huge signal in my detector because I'm going to maximize the phase, to synchronize the phase of all the emitters to all the atoms in my system. Now, let me do this in 1 dimensions first. I hope I can, yes, I can probably. And I'll stop in a couple of minutes. Let me do this in 1 dimensions, okay, which is much simpler. So in 1 dimensions, I have my points here. They are spaced at the distance a. So if I place the origin, say, here, the positions are I, and suppose I label the i's as follows: 0, 1, 2, -1, -2, and so on and so forth, okay? And use that I to label the positions from -infinity to +infinity. Then the position of atom I is given by A times I, right? Because atom I0 is at 0, atom 1 will be at A, atom 2 will be at 2A's, and so on and so forth. Atom -1 will be at -A, and so on and so forth. So let me remain in 1 dimension and look for possible values of a number G such that this is true for every I, that is, for every Ri. That sounds much simpler as a problem, right? What is the solution to this problem? How can I make this one for every integer? What do I need to do to this to make this one for every integer? 2 pi. In fact, not only 2 pi, but 2 pi times any integer. Right? If G times A is 2 pi times an arbitrary integer, I'm done. So I've been able to solve this problem. I've been able to find an infinite number of G's, 2 pi over A times an integer, that satisfy my condition. Not only one, not only two, an infinite number of them. And they all satisfy this condition. Yeah.
Since I is an integer, so do we need another integer?
Sorry, do we need another?
I is integer, right?
I is integer, yes.
So, yeah, this is true, but
The question is whether there are more.
no, I mean, okay, is it necessary to put n? Because
No, what I'm saying is that certainly any number of this kind satisfies this condition. I'm looking for all the possible values of G that satisfy this condition. 2 pi is okay, but I can do more. I mean, I can find all this. The question could be, are there more values of G that cannot be written in this form that that I'm not considering yet? Well, the answer is no. I mean, whatever number I take, which doesn't make 2 pi here or 2 pi of an integer, will not make one for every I, right? So that's really all and only these numbers make my phase equal to 1 for all points in the Bravais lattice in 1 dimension. So we're doing the 1D example now. And we've been able to find an infinite number of them. Number of points that satisfy this condition. Okay, I think it's a good point to stop, and next time we're going to see how this can be rephrased in 3 dimensions. The obvious answer is that yes, it is possible to do it also in 3 dimensions, and I will give you a prescription for how to find the set of G's that satisfy this condition for all the Ris, also in 3 dimensions. And they're going to be very similar to these ones in 1 dimension, of course. Okay? Any question? Yeah? Sorry, we?
We found
Yeah.
this relation.
Right?
Is, we want to maximize the
Yes,
signal.
yes, correct.
Why we want to maximize?
Okay, that's a very good point. It's just the beginning of an exercise that we are doing. So I want to find, for example, if there is a way to maximize the signal that I see at my position. Your question is, what if the signal is not, say, maximum? What if the phases don't add up in this way? We're going to discuss it later on, if you don't mind. We're going to find, let me anticipate what we're going to find. We're going to find that the signal can either be maximum, like this, or essentially close to zero. So when I play with my K out, I cannot play with K in because that's given. I can play with K out because I can move my detector. I can also play with K in because I can decide to change the wavelength of the radiation in principle. So, okay, when I play with K in and K out, either by moving the detector or by changing the wavelength of the light, there will be specific values of K in minus K out, that is, these vectors, for which my signal has a huge intensity. All the other values of K in minus K out will give me essentially zero. Okay? So I will have suddenly some peaks in, in my detector when this condition is met. Otherwise, the signal is close to zero. It will be like a random distribution, yes. As soon as you will see, I mean, you see it also from here. Suppose that you're able to satisfy this condition, okay? Suppose. Now, suppose I add an arbitrarily small delta G to this, okay? An arbitrarily small one. Then what's going to happen is that I have my 1s times delta G times R, right? But this delta G here is not going to be something that makes this 1. It's going to be an arbitrary number, right? So this phase here is immediately going to kill me when I sum it over R, regardless of how small is delta G. Okay? Because I'm adding phases in a way that eventually, if I sum R over a large number of R's, of course, will make this object arbitrarily small, because they will add up in not in phase. Okay? So I'm going to see a signal only in correspondence, only when this condition is exactly met. Otherwise, I'm going to see something which is close to zero. Any more questions? All right. So we'll see you on Friday.